Hi boys and girls, it's Mr. Wasemann, and today we are going to be looking at story problems that involve decimals. We're in our math journals on page 292 and 293. And before we jump into the problems, some of you might be wondering, well, why are we dealing with decimals right now? We've been doing a lot of work with mixed numbers and fractions. Well, to answer your question, decimals are just a form of fraction notation. Let me give you an example or work out a model so that I can demonstrate what I'm talking about. So a fraction, of course, is just a representation of an amount that is less than 1. So if I have a rectangle here, and if I were to divide it, say, into 10 sections, like so, each part of my fraction would be a tenth. And I would represent that like so. The denominator is out of 10 because there are 10 possible parts. Now, if I had 3 parts that were shaded in, like so, my fraction would then be represented as 3 tenths. 3 represents the number of shaded parts versus the number of total parts possible. Now, when we are dealing with decimals, decimals is just a different way of representing the same amount. We would represent 3 tenths like so, 0.3, and we do so with the understanding that our number system is what we call a base 10 number system. That means that we have grouped place values into groups of 10. So we can have from 0 to 9 exist in a place value before we regroup and create a bigger place value. And that is true with fractional parts. So when I look at my decimal representation of this picture, 3 tenths, what I'm looking at is my numerator 3 is now to the right-hand side of my decimal point here. And that line that divides numerator and denominator, that has been replaced with this dot, this period. Okay? So when I see 0.3, I am looking at a fraction 3 tenths of a whole. An easy way of thinking about that is in terms of money. What's 3 tenths of a dollar? Well, that would be 3 dimes. It takes 10 dimes to make up $1. Now, if I were to represent a different amount, let's say I completely fill in this rectangle, that would be 10 tenths. And then let's say I added one more, tenth, and that would make it 11 tenths. Oops, that did not fill all the way. There we go. So 11 tenths can be represented in a number of ways. I put the 11 as my numerator over the denominator, but it also can be represented as one whole. That would represent the entire rectangle, and then 1/10, the extra tenth that's off to the side, 1 and 1/10. Now, to represent that as a decimal value, I would write it like this, 1.1. And again, what I'm doing here is I'm taking my whole number and I'm putting it to the left of the decimal. And then I'm going to put my fractional part, the numerator, to the right of the decimal. The decimal, of course, represents the difference between wholes and parts. So 10 tenths would be the same as one whole. So one whole would live on the left-hand side of the decimal because we are now in whole number territory. Okay? Now with that understanding, what we want to do is we want to solve for some number stories that involve decimal values. So let's take a look at number 1. Deja draws a line segment that is 6.5 centimeters long. Then she makes the line segment 2 centimeters longer. How long is the line segment now? Let's employ our ruckus strategy and read this again. Deja draws a line segment that is 6.5 centimeters long. Then she makes a line segment 2 centimeters longer. How long is the line segment now? So we reread it, we circled the important information, we underlined the question, now we need to come up with an action plan. Well, the word longer tells us that we need to add. She is adding 6.5 to 2.7. So when I set up my problem to do my scratch work, I need to line up my numbers. And this is going to be important to set up our problems vertically so that when we have our numbers set up, that the decimals and the decimal place values correlate. Okay, I want my tenths to add to my tenths and my whole numbers to add to my whole numbers, and if there's any regrouping, I know where to put the numbers. So let's take a look at this. 5 tenths plus 7 tenths is going to give us 12 tenths. So I put the 2 down here, and I'm going to carry the 1. Now I'm adding whole numbers. 1 plus 6 is 7. 7 plus 2 is 9. So my total is 9.2 centimeters. 9.2 centimeters. So let's write that up here in my space. Now, the way I approach adding 6.5 and 2.7 would be the same way I would approach the same number if they were whole numbers. Oops, not 67, it's 65. If I was adding 65 plus 27, I'd do it the same way. 5 plus 7 is 12, carry the 10, 10 plus 60 is 70, 70 plus 20 is 90. So without the decimals, it would be 92. Well, 92 centimeters is a far different amount than 9.2. So that decimal point right there makes all the difference in the size of the answer. So we need to make sure that we are lining up our place values, especially our decimals, to make sure that we are adding the right place values. So when you're approaching an addition or a subtraction problem like you are in problems 2, 3, and 4, you need to make sure that you are lining up your place values and doing your operations vertically. Now let's take a look at number 5 real quick. A newborn baby weighs 3.4 kilograms. A newborn hippo weighs 9 times as much. How much did the newborn hippo weigh? Okay, so now what we're doing is we are multiplying with a number that has a decimal involved. Now again, we're going to approach this problem the same way we would as if there was no decimal. Okay, so let's reread this problem again. A newborn baby weighs 3.4 kilograms. A newborn hippo weighs 9 times as much. Okay, the word times is a dead giveaway. That tells us we're going to multiply. So how much did the newborn hippo weigh? So we need to multiply 3.4 times 9. So right now what we're going to do is we're just going to ignore the fact that 3.4 has a decimal. So I'm just going to write it as 34. 34 times 9. So if I use the partial products approach, I would multiply 30 times 9, and then 4 times 9. Well, 3 times 9 is 27, so 3 with a 0 behind it times 9 is going to give me 27 with a 0 behind it, or 270. And then 4 times 9, of course, is 36. So I've lined up 270 plus 36, and then I add 0 plus 6 is 6. 7 plus 3 is 10, so I'm going to carry that 1, and then 1 plus 2 is 3. So 34 times 9 would give me 306. Now, let's look at that same problem again, but this time we're going to involve a decimal. The decimal between the 3 and the 4. So what that does is that now changes 30 into 3.0, and it changes 4 into 0.4. So 3 times 9 is 27. So 3.0 times 9 is going to be 27.0. And then 0.4 times 9 is going to give me 3.6. So basically what I'm doing is I am remembering that there is a place value difference between 3 and 30 and 4 and 4/10, and that's what that decimal is representing. So when I represent my total answer, it's not going to be 306, it's going to be 30.6. I got the answer the same way I would as if I were multiplying 34 times 9. I am just moving that place value over. Okay, so my answer is 30.6 kilograms. And that's a big baby. If you have questions about these problems, feel free to reach out to your math teacher. Otherwise, we will talk again soon. Thanks.